Boa tarde, meu nome é Hugo Aguilani, eu dirijo o Instituto Serra Pilheira. O Instituto Serra Pilheira é uma instituição privada que apoia a ciência e divulgação científica no Brasil. Nós ajudamos o INPA a organizar esse ciclo de palestras públicas aqui no ICM. Hoje, nosso palestrante é francês, igual eu, e chama-se Cédric Villani. O Cédric tem uma história singular. Ele se formou na École Normale Supérieure de Paris, tornou-se um matemático reconhecido e conseguiu a medalha Fields em 2010 na Índia. Logo depois de ter ganhado a medalha, Cédric começou a fazer divulgação científica e tornou-se uma referência na França e no mundo, parecido com o Etienne Gis, que fez a palestra impressionante sobre flocos de neve na semana passada. Hoje, a palestra do Cédric se chama A Idade da Terra, quando a Terra era jovem demais para o Darwin. É muito especial para mim apresentar essa palestra hoje para vocês por 3 razões. Primeiro, eu sou geneticista. Eu sei que um dos grandes problemas que o Darwin encontrou para validar sua teoria da evolução foi calcular a idade da Terra. Naquela época, o Lord Kelvin, que era um físico britânico, pensava que na idade do planeta era muito mais jovem do que ela realmente era. Estou muito curioso de saber como a matemática ajudou a resolver esse problema. A segunda coisa é que hoje eu estou apresentando o Cédric aqui no Rio, mas eu trabalhei alguns anos na mesma instituição que ele, na École Normale Supérieure de Lyon. Eu trabalhava no 2º andar, ele trabalhava no 4º. Então, é especial. E, finalmente, o Cédric representa um tipo de cientista, cientista cidadão, que o Instituto Serra Pilheira procura. Não só ele se preocupa com divulgação científica, mas ele também se preocupa com vida pública e política. Ele se preocupa tanto com a vida política que ele foi eleito deputado da França em 2017 e atua até hoje no parlamento francês. Cédric Villani.
Merci, Hugo. Thank you very much, Hugo, for this great introduction. So, this lecture will be about a problem which is mixed of various subjects. There will be mathematics, there will be physics, there will be geology, there will be biology. We'll see all these together. It will remind us that in real life, scientific problems do not fall very clearly in one category or another. They may be a mix of various subjects. Also, it will be an opportunity to see that mathematics is everywhere, and even in some problems that we would never think are part of it. This one is an example. We'll talk about the age of the Earth. What the hell is there for mathematics in this? We shall see. Also, this lecture will be an opportunity to see how much scientific points of view may change from time to time. And also how even the best scientists of the world can be completely wrong sometimes. Whenever you have the impression that you are mastering your subject and ready to give an authoritative answer to some big debate, please remind yourself of the story that you will see unfolding, reminding you that even the absolute best can be wrong sometimes. Along the way, we will see some of the themes that are very close to my heart of scientist. We will talk about mathematical physics and the power to use abstract equations to understand the real world. We will talk of Fourier analysis, which I have taught for many years at École Normale Supérieure de Lyon, that Hugo was mentioning in his introduction. And it's a subject which I have taught to mathematicians as well as non-mathematicians. And we will talk about partial differential equations, which are differential equations governing the world in many respects. This is supposed to be a broad audience lecture, and so I will be very pedagogical and explain quietly in detail what is meant by the various mathematical objects. But first of all, let me insist that it has been for several thousands of years the idea that mathematics can be useful to understand our Mother Earth. Maybe the most famous example from ancient times is the one of Eratosthenes. By the way, as you noticed, my slides are written in French. Since a big part of the audience is Portuguese speaking, I thought it would be stupid to translate from French to English the written text, since English is much more different from Portuguese than French. So between the English that I am speaking, the French on the slides, and the Portuguese in the translation, hopefully you will understand the meaning. Anyway, this is Eratosthenes. Eratosthenes had this wonderful, simple and efficient idea to measure the Earth. And we learn this in school sometimes nowadays. Eratosthenes knew that there was this city, in the city of Alexandria and in the city of Sienne, or Aswan, a very interesting configuration. In this very interesting configuration, here there is a well in Aswan, and at a certain day in the year, the light goes to the bottom of the well. So that we know that the rays of the sun are exactly vertical at that moment. And you also knew that Alexandria and Sienne were on the same meridian. So putting a big stick or gnomon there in Alexandria on this particular day, if you measure the angle that the rays of the sun make to the vertical in Alexandria, you will know exactly the angle viewed from the center of the Earth of Aswan and Alexandria. And if you measure the distance then from Aswan to Alexandria, maybe going on a camel's back, measuring, you will be able, by simple proportionality, to get the distance all around the Earth. And how do you measure the angle in Alexandria? Well, it's basic trigonometry. If the angle is small, the sun is high, the shadow is short. If the angle is large, which means that the sun is low, the shadow is long. The ratio of the length of the shadow to the length of the stick will give you access to the angle through inverting the tangent. So simple and so efficient. It is said that the estimate of Eratosthenes was accurate up to maybe a few percent. We don't know exactly which is the precise unit that he was using, but it's very likely that the estimate was very close to the truth. And this is in enormous contrast with the view that Eratosthenes had about the geography of the Earth. This is the map of the world according to the same Eratosthenes, who was both mathematician and geometer. Well, look what Africa is reduced to. We don't recognize Asia. America does not exist. Brazil is not on the map, I'm afraid. He had no idea of all that. And in spite of this ignorance, he was able to get the length right, using the mathematics to measure what seemed to be infinite, but what actually could be computed. There is a lesson here which comes again and again in applications of mathematics. Mathematics allows you to go beyond what your senses or your experience tells you. And even if you've never been to some place of the earth, you know that this place of the earth obeys the mathematical laws. And it will appear in the mathematical computation for the size of the Earth, even if you don't know of it. Similarly, mathematics allows you to go to infinitely small or infinitely large amounts of space, of distance, whatever. Think of the planets. The small planets, they look rather familiar in the sense that their dimensions are comparable to those of the Earth. And when you see Venus, and we know that something is true on the Earth, maybe the same kind of thing will be true on Venus. But some planets are much bigger, like Jupiter. It's difficult to think of such a monster planet as Jupiter. You see the kind of eye on the surface of Jupiter, which is actually a big storm going on Jupiter forever. It's bigger than the Earth. Must be very difficult to think of how it is to travel around Jupiter. But Jupiter is so small in front of the sun, or a big star, like Sirius. And Sirius is so small compared to Aldebaran, or some other real big star. And even Aldebaran is very small compared to a super big star, like Betelgeuse. At this scale, the sun is even invisible for the eye. These kind of stars are like worlds that our mind cannot even think of, and at distances that our mind is unable to think of either. Still, for mathematics, there is no problem to put these in equations and to predict the motion of these stars, even though we will never, ever go there. So mathematics goes beyond our intuition. Think of this also for the story that will unfold now about the age of the Earth. How can we think of the age of the Earth? Certainly it is much larger than the scale of a human life. And it is natural, in the end, that at some point, some mathematics enters this problem. Other big questions which have been put to the test of mathematics and are still being discussed even today are questions such as, what will the solar system become? Or what will our galaxy become? Part of my research was related indirectly to that third problem. It would be a whole talk to explain you why. Here are some of the amazing scientists who thought of how mathematics could help attack these questions over the centuries. Some of them will be heroes in my lecture, focusing on the first question, the age of the Earth. The first serious attempt to compute the age of the Earth came not from the scientific sphere, but from the religious sphere, and from James Ussher, the chief of the Irish Anglican Church at some point in the 17th century. In one of his books that were very important at the time, he makes a very detailed analysis of the Bible, the Old Testament, to find what was the age of the Earth. Starting from the postulate that the answer had to be in the book. This was not an easy task, also because there are several versions of the Old Testament, slightly different. And if you want to establish a fine chronology, you have to do some tricky comparisons. After enormous work, Ussher concluded that the Earth was created 4,004 years before Christ. When we see this nowadays, this figure, it can make you smile. I saw some of you smiling in the audience. If we want to be a bit, nasty, we may say that the first digit is right, like the 4, because nowadays we learn in school that the age of the Earth is about 4.5 billion years. And then we may say that the number of digits is wrong. It's not in the order of 1,000, but in the order of a billion years. And so there are like 9 factors of 10, 9 zeros if you wish, which are missing. And of course, it would be stupid to laugh at Usher, a very intelligent and, by the way, very tolerant man who did absolutely the best that he could, given the source and given his postulate that the answer had to be in the Bible. For a long time, this would remain the official date of creation of the earth for the church. Now let's jump in time and go to the 18th century in France with Georges-Louis Leclerc de Buffon, a scientist versed in many fields, but in particular biology, botanics. He tells us a completely different philosophy of the world. The answer is not in the Bible, but the answer is in experiments that you can do with the natural world. He says it is with fine experiments, carefully thought of and followed, that you force nature to uncover the secret. Every other method has never succeeded. So Buffon tried to apply this reasoning to the age of the earth. But how can you make experiments? First, you need a model, a way to represent the earth, in the language of physics, say. And like before him, Newton or Leibniz or Descartes, Buffon says that the earth should be thought of as a ball made of, say, metal, say, like iron, with the heart that would be in fusion, extremely warm. And it should be cooling down. We may wonder why, even in those days, they thought of the center of the earth as very, very hot. For sure, yes, the center of the earth, very, very hot. First, of course, there was the clue given by the volcanoes. But also, it was known that whenever you go down the earth, for instance, in a mine, the temperature increases and increases. And whatever mine you go into around the world, it is the same kind of increase. So giving the idea that temperature increases all the way when you go down the earth. Now, a model for this can be found in a cooking analogy. Imagine that you bake a cake that is like a ball. Your cake goes out of the oven. Initially, it is very, very warm, all of it. But then the surface cools down faster than the center. And we know this from our experience, because if we are too confident in the fact that it is cooled down and we bite into the cake, we may burn our tongue because the inside is hotter than the outside. And there is the idea that the Earth is like this, like one of these big cakes, enormous cake, except that it is made of iron or something like that. The center is still very warm, and the outside is cool, is what we know. And so now that it has a model, Buffon can search for scientific laws relating the size of the cake to the time of cooling. Maybe a small ball will cool down fast, a bigger ball will cool down slower, etc. And doing experiments on bigger and bigger balls, you may find a mathematical law that you will be able to extend to the real Earth. This was the reasoning, and he worked on this. And he found this figure, 75,000 years. Now, my friend, this is a bit disappointing, don't you think so? Buffon told us these big words about unraveling the secrets of the Earth. And in the end, his estimate is only 1 order of magnitude better than the one of the Bible. There are other things that are weird in the Buffon results. Okay, so this is an extract from his text. Just look at the figures, the numbers. 4,026, 46,991 years, 100,696 years. You know, this is experimental physics, and the device used by Buffon is so crude that the accuracy is certainly not better than 1 order of magnitude at best. So why is it that Buffon gives numbers up to 6 significant digits? If a student in high school would put such figures in a problem of physics, even if the numbers are mathematically right, the teacher should count that it is false, because it's a mistake in experimental physics to announce more accuracy than you can demonstrate. One explanation for this weird accuracy of the results is that Buffon was not very familiar with this idea of how much accuracy you can guarantee. Theory of errors developed mostly in the beginning of the 20th century. Another interpretation is that he wants to impress people with very precise results. It's a very classical strategy that nowadays also many people use around the world, especially when it goes into politics, I have to say. Also weird is the fact that Buffon, in private, acknowledges that the real result should be much bigger, like millions of years. But this he does not dare to write. This is 1779. We are still in the ancient regime, as they say. And you may at times disagree with the church, but not write it too explicitly. And remember, for the church, the official date is still minus 4004. How does Buffon reconcile his result of 75,000 years to the official results? Well, he uses the rhetoric, like saying, I know that the earth was created in 4004 BC, but let us play a game. Imagine that the laws of physics would apply, etc., etc. Okay, enough for Buffon. Let's move to the next hero, Joseph Fourier, who is one of the icons for people who hope to do good science and good politics, because he was both. He was a pioneer of the study of partial differential equations and mathematical physics. His theory of signal is used all around the world for image processing, for sound processing, and is a whole branch of mathematics devoted to it. To explain his contribution to the problem of the age of the Earth, I will recall that the differential is when you have a function and you're interested in estimating how fast this function changes, you may look at the variation rate or the slope. And it's very easy. If you have your function which is varying, you make a close-up and you look at the tangent to the curve. And you look at the slope of this tangent. In this example, in this tangent, whenever you go 1 unit to the right, you go up by 0.8 units, which means that the differential value is 0.8. And it quantifies the rate of variation of the curve, of the function. Now, for any point on the curve, we may compute the value of the derivative or differential. You see below a curve which is the curve of the differential. For instance, when the slope is 0, the value of the curve below is 0. And then we may take the derivative of the derivative. And this will be the second derivative, or second differential. In physics, the first derivative corresponds to the speed of variation, the second to the acceleration. Now, with this in mind, we will define partial differentials. When you have a function or signal depending on several variables, we may look at the slope of variation in any one of these variables. For instance, think of the temperature in the air. It will depend on the time or on any of the three coordinates that will tell you where we are in space, x, y, z for the position. And we look how fast it varies with respect to time. It will be the time differential. And if we look at how much it will vary with respect to position, or say to the x variable, it will be the x differential. These are partial derivatives or partial differentials, and it's a major discovery of physics in the 17th and 18th century that many phenomena in our world are described and governed by equations relating partial derivatives of functions. Fourier is one of the early promoters of this point of view and thought of defining a theory of a heat evolution based on these principles. So I said this is the credo of partial differential equations, with equations relating the slopes or tendencies with respect to the various variables. You can model physical phenomena. Here is the heat equation, one of the most respected equations in mathematical physics. When I started my studies of partial differential equations, this is one of the first that our professor explained to us. How does it go? The unknown is the temperature. For instance, you have a big ball with some points which are hot and others which are cold, and you want to understand how the heat will change according to time. And that's the equation by Fourier. On the left, one time derivative. On the right, second derivative in the position variable. So on the left, it's like a speed of variation. On the right, it's like an acceleration, except that the variable is not the time, but the position. And to relate these two partial derivatives, there is a coefficient C, which is the thermal diffusivity, which represents the physics. Maybe some material will cool down very fast, and others much slower. It depends on the physics. Now, the idea of Fourier is let us use this equation to understand the age of the Earth. See the change of point of view. First, we tried to find the solution in the Bible. Second, a physical model with some analogies, and now some equations allowing you to put the problem in mathematical terms. X here can be one dimension or two dimension or three dimension if we look for the Earth. let's look at how it works out on computer simulations. Computers don't understand this language of analysis and differentials. But we may transform this in discrete forms that they will understand. And so here we go. So look at this example. Imagine I want to look at the heat inside the long stick. Some parts of the stick are hot, color is in red. Some parts are cold and colored in blue. And here you see the graph of the temperature initially. And now, after preparing the stick in this condition, I will let it cool down. See how the temperature will evolve. Okay, what did we see? First of all, globally it goes down. If we would wait for a very long time, it would end up completely flat. But it will take quite some time, corresponding to the very cold stick. Second remark. Even if globally it cools down, some parts of it start by going up. You see this point here, here, and it will first go up for quite some time. And only after that it will go down. Third remark. First, the heat profile was very rough. And immediately it was irregular. But just after that, it starts being quite smooth, like a mountain which has been eroded. And the final remark I will make, at first, it varies very fast and then very slowly. So in the second half of the movie, we get bored. All these phenomena are part of what mathematicians study when they study the partial differential equations. To understand qualitatively the evolution of physical phenomena. It can be heat, it can be fluids, it can be quantum mechanics. All this is part of the qualitative analysis of partial differential equations. And because it starts you see it starts slowly, it starts fast, and then it slows down. It will be even more clear if you run the movie backwards, and we will see things getting faster and faster. So the variation is not the same at the beginning and at the end. Fourier thought we may use this to decide if the Earth is young or old. Let's go on with the simulation for the heat in the Earth. Imagine this is the Earth, and the heat profile is here on this graph, which has been rotated. The temperature at beginning is very high everywhere. And we will let things cool down, as if it's the cake that we get out of the oven. Look at the heat profile. The center remains very hot. The outside is cold. The curve becomes more and more like a bell shape. Actually, for those who know, it resembles a Gauss curve. How can we use this profile in our problem? Look carefully at the initial slope of the graph near the endpoints. These slopes are shown at the up and down parts, and they move monotonically. Very high at the beginning, and then lower and lower. These slopes are very interesting because in real life, it corresponds in this model to the speed of increase of the temperature at the surface. So if we measure that speed of increase, we'll have information about the age. If the increase is slow, it will mean that the Earth is old. If the increase is fast, it will mean that the Earth is young. That was the reasoning of Fourier. And to measure the speed of increase, basically we go down the mines and we make temperature measurements. This is the idea. And Fourier put this with all assumptions, neglect the fact that the Earth is round, and imagine that it is flat. It looks horrible, but actually does not change much. No heat source inside the Earth. This is an assumption. The Earth is globally like a big sphere, a big ball made of iron. At the origin of the Earth, the temperature was uniform, and the temperature remains constant on the surface all throughout times. These are the assumptions. And Fourier had no computers, of course, but he was very clever and discovered how to compute from these assumptions the rate of increase of temperature around the surface inside the model. And here is the formula that he found. This gradient, which is the rate of increase of the temperature, is equal to the difference between the initial temperature and the outside temperature divided by square root of pi times the diffusivity times the age. Beautiful formula. In retrospect, we may say that it was a bit too beautiful. When you find something beautiful, you are inclined to believe in it very easily. Now, if you invert, you obtain time as a function of the diffusivity, the temperatures, and the gradient. And maybe T0 is the temperature of fusion of the iron. Maybe TE is our temperature around us. Gamma you measure going in the mines. C depends on the physics. And pi is about 3. Beautiful. Now, what is the result obtained by Fourier? Amazingly, Fourier does not do the computation. He stops here and says this is a great number of centuries. This is very strange. We may only make assumptions about why Fourier did not do the computation in the end. My personal theory is that Fourier thought to himself, "Oh, I'm very proud of my clever computation. But maybe I missed something in the assumptions. And maybe the result is not right. Now, if I make a computation, a numeric computation, people will focus on that result and may only remember that I was mistaken. While if I only give the formula, people will recall my clever reasoning and formula." If such was the case, congratulations, Fourier. Anyway, let's jump now 4 decades to arrive at the climax of our story. When William Thomson, also known as Lord Kelvin, again goes into this problem of the age of the Earth. Thomson was a physicist and an inventor, a great one, maybe the greatest of all in his time, after the death of Maxwell. He made devices like this galvanometer, theoretical results of mathematical physics, there is a theorem of Kelvin in fluid mechanics. He made an harmonic analyzer that is an ancient precursor of our devices to analyze the sound, for instance. Etc. He made up great concepts and great inventions as well. Maybe the most famous of his inventions is the way to construct refrigerators. Thanks to the effet Joule-Thomson, which is part of thermodynamics. But also, he was instrumental in helping engineers lay down the first transatlantic cable that allowed reliable communications between Europe and America. Nowadays, Kelvin, in his honor, is the scientific unit for temperature. But also, there is a special brand of refrigerators called Kelvinator. Kelvinator. You know, like the Terminator of heat. I think it's a great destiny if you get transformed into both a unit of physics and something like the absolute device for creating the cold. Thomson was very much interested in the age of the Earth. And wanted to continue the computation of Fourier. And he finds, with the best possible estimates of his times, that the Earth should be aged of 40 to 200 million years. We may say, okay, that is not bad. We are not far now from the billion-year scale. But it was posing great problems to fellow scientists, actually. This estimate was actually shorter than what the geologists of his time had come to believe. Indeed, in the 18th century, the so-called gradualists had come more powerful. They had become stronger. Like Lyell and Hutton, they believed that the world was evolving on a very, very, very slow time scale. No vestige of a beginning, no prospect of an end. And all of a sudden, the physicists' estimate was posing a problem to them. After all, they managed to adapt their scales. But there were other people who could not adapt. This was a new kind of scientists, evolutionists. Darwin, Wallace, their theories did not match with the estimates of Kelvin. Here is, on the left, Lord Kelvin, the most famous physicist of his time. On the right, Charles Darwin, the most scandalous scientist of 19th century, with theories that are in direct contradiction. Darwin needs several billions of years for his theory of evolution. Kelvin says the Earth is, at best, 200 million years. Who will win? It's like a box match, you know. In 1893, Kelvin works again, improves the reasoning, or that's what he thinks, and finds 24 million years. Now, at such a low estimate, even the geologists say, stop. That is impossible, we will not buy it. This was a major scientific crisis, dividing scientists, those believing in a young Earth and those believing in an old Earth. Good to remind us that the history of sciences is made of a lot of controversies and debates. It's very good to read some of the comments in this controversy. Huxley, who was on the Darwin side, says mathematics is like a mill that can grind things to very, very fine degree. But if you give it P, you will not end up with flour. What you get out depends on what you put in. And mathematics is like this exquisite mill. Even if the reasoning is very, very clever, wrong assumptions lead to wrong conclusions. Nowadays, we have a good way to say it. Garbage in, garbage out. Mark Twain makes some comments, like Lord Kelvin is the highest living scientific authority, so we have to all accept his views. It's very difficult to say if he means this seriously, or maybe second degree, or third degree humor. You know, he was a twisted guy. But this quote shows you that even people outside the scientific world were aware of the controversy. Various people obtained results more like Kelvin, including Darwin's own nephew. And after 15 years of debate, the church decides now it's time to get rid of Usher. Not taking sides for Kelvin or Darwin, but removing the minus 4004 official date of birth. Depending on your personal inclinations towards church, you will find it a scandal that they waited so long, or after all, as a sign of progress that they are ready to change the official speech from time to time. Lord Kelvin, in spite of his great intelligence, does all the mistakes that you should never do in this controversy. He uses big words like impossible. He insults his opponents, saying they are of bad faith. He gives his opinion on specialties which are beyond his. Like he says that evolution theory should not rely on Darwin's principles. Even doubts that evolution took place. Here is a famous quote of his. Overpoweringly strong proofs of intelligent and benevolent design lie all around us, which is made it that Kelvin is now quoted by people from the intelligent design movement, which is an anti-scientific way to talk about evolution as a process which is like guided from God. Make no mistake, who knows, maybe in evolution was guided, you may believe in this, but this is belief, not science. Darwin, on the contrary, does a great argumentation. Darwin argues in a great way. He says, okay, about the time that elapsed, it seems that it was insufficient for the amount of change that I assume. This objection is put forward by Sir William Thomson and is one of the gravest so far. He doesn't try to minimize. He says, okay, this is a very serious objection to my theory. But please, you have to agree that we don't know at which pace the species change. Of course, in those days, genetic mutation, nobody could think about it. And secondly, what do we know about the making of the universe and about the inside of the Earth? We are not sure of what really there is there, so that we can really speculate about its age. In 1904, New Zealandese Ernest Rutherford managed to reconcile everybody for wrong reasons. So first we have a big controversy, and then somebody resolved it, and the resolution turned out to be for bad reasons. To not go too over time, I will not say much about this episode, but I encourage you to look up in the books the anecdote of how Rutherford managed in a session of the Academy of Sciences in Great Britain to get the agreement of Lord Kelvin by framing him as a prophet so that he would be very pleased. Anyway, Rutherford was among those who discovered radioactivity. Radioactivity is a natural source of energy. Energy and heat come hand in hand. So if there is some sources of energy inside the Earth, it means that there is sources of heat inside the Earth. And so the computation of Fourier, which assume no source of heat, does not work. This was the explanation that Rutherford suggested. And everybody accepted this. And to this day, many people are convinced that this is the reason why Kelvin had it wrong. But actually, that is not the case. And if you redo the computation with the radioactivity, it does not change so much. So where was the mistake? Actually, the mistake had been found as early as 1895. But nobody paid attention. Here's the guy who understood the mistake, John Perry, who had been an assistant to Kelvin, suggested that in fact the interior of the Earth should be viewed as a liquid, not as a solid. Heat in a liquid and heat in a solid are very different. The equations that I showed you are all about the heat in a solid. Why is it different? Here is an image. All of you are sitting on your chair like the atoms in a solid. Heat is like agitation. Imagine that the first row starts to be very much agitated, going in all directions, and also, banging on their neighbors from behind, etc. Transmitting their agitation to the next row, that will transmit it to the next row, etc. That is how heat goes inside a solid. In a liquid, it's very different. The particles in the liquid are not sitting in their places. They can move around. If you were particles of a liquid, very agitated, you will jump all around and go agitate here and there, like the dancers in the opening ceremony, and communicate your agitation in a much more efficient way behind. This is convection, as opposed to diffusion. And convection goes much faster. Equations are different. The whole reasoning is different. Now, why did Kelvin not think of the convection? He ruled it out, showing that inside the Earth, it is like a rock solid. And a rock is not liquid. But here comes the mistake. Remember what I told you in the very beginning of this talk. When you go to things that are beyond your intuition, let the mathematics speak, not the intuition. On a very, very, very long time scale, like billion years, even the rock may behave like a liquid. On a very, very, very slow time scale. And that indeed is what happens inside the Earth. Here is what Perry says. I know that solid rock is no wax of shoemaker. But 1 billion years, it's such a long duration. And forces are amazing. It's the power of the enormous time that makes the Earth inside behave like a liquid, even though it is made of solid rock. Now, my friends, let us pay tribute to John Perry as the first human being who was able to find the correct order of magnitude of the age of the Earth through a scientific reasoning, like billion years. And it's a sad story that nobody believed him, which also has to teach us a lesson. He thought the Earth was like 2 to 3 billion years and explained what was the reasoning behind this. He was not listened to. And up to about 1960, scientists believed in a solid Earth. That is also crazy, my friends. In 1960, we knew how to make atomic bombs. We knew secrets of the infinitesimal world. But we still did not know what was inside our Earth. Of course, there had been a few exceptions. Most importantly, Alfred Wegener, who was a proponent of the theory of the liquid center of the Earth and of the continental drift, which up to the middle of this century was a theory. And it's amazing in retrospect to think that people thought that it was just a coincidence that the tip of Brazil would fit the inside corner of Africa. And nowadays, it's all embedded in a consistent theory involving geology, physics, mathematics, but also biology through the evolution. And the mistake of Fourier and Kelvin was not in the math. They made beautiful math, formulas which are still valid. It was in the assumptions. They believed that the Earth was homogeneous. We now know that it's made of layers that are changing. Some of them should be considered as solid, some of them as liquid. And that is our current guess of the curvature of the temperature inside the Earth. Does not look like the one we saw. So let's remember this also. We may compute something with very high accuracy, but sometimes we're computing with very high accuracy the solution of the wrong equation. Nowadays, we have computers of amazing technology that enable us to do all kinds of computation. But remember, even if Kelvin had had the same computers as us nowadays, he would have made the very same mistake. And nowadays there are people who tell you that computers will replace science and that there's no use to learn about the models and the equations. Quite the contrary. The more precise is your computation, the more you have to understand what exactly you are computing. That is all. Thank you for your attention, and I hope you retain some of these stories for other appreciation. Here I put a few references for whoever wants to know more. Thank you.
Infelizmente não tem tempo para pergunta, mas agradecemos mais uma vez ao Cédric. Obrigado.
Thank you very much.